I want to finish talking about the efficiency gap. I don't have all that much more to say about it, but I thought we'll just do one more example, and then we'll move on to the next thing. So this is the efficiency gap, which is what we started talking about last time. And remember, the efficiency gap measures packing and cracking. So it's meant to be a neutral statistical way that you can measure and see if the districts are fair or not. All right, and how it works? Well, let's just do another example. So I thought we should do one that's a little more realistic. All the examples we did last time were kind of made up examples. But this will be a more realistic one using real life numbers. This is in the state of Oregon, the United States House of Representatives. I wrote house with a W. House. The U.S. House of Representatives. The state of, and I took these numbers from 2022. All right. And the state of Oregon has 6 representatives. There are 6 districts, and these, I'm going to write the numbers in thousands. Just, I rounded everything to the nearest thousand. All right, so I have to just straight up tell you what the votes were in each district. I said there were 6 districts, so I'm going to make a big chart here. And of course, the parties, the only parties that really matter on the large scale are the Democrats and the Republicans parties. And I'm going to tell you, in District 1, the Democrats got 211,000, and the Republicans got 99,000 votes. All right, these numbers I just looked up somewhere. In District 2, it was 100 for the D's and 208 for the R's. In District 3, it was 212 and 80. In District 4, 171 and 146. In 5 was 171 and 178. And in 6 was 147 and 139. All right, so this much of it I just looked up. You will just have to take my word for it. These were the actual numbers. All the rest you can calculate on your own. So this much, you just have to be given that information. But from there, we can calculate the efficiency gap. And we're going to do what we did last time. It's just the numbers this time are bigger and slightly weirder. But what we have to do, so I made this big chart last time. The total and the threshold, that is, the total will just be the total number of voters in that district. So you just, for each of these, I'm just going to add the D plus the R. And 211 plus 99 is 310. If you're doing big numbers like this, feel free to use a calculator. On our tests or something, I will give them as simple numbers, although this isn't so bad. The total for District 2 is 308. I could do that one in my head. This one is a 292. The next one I added ahead of time, I got 317. The next one I got 349. And then the last one I got 286. So this is just each time add the D plus the R. Hope everybody sees how I did those. And then the threshold each time. So the threshold is always half of the total, and then you go plus 1. So 310, I would do half of 310, which is 155, I guess, and then add 1 to make it an actual majority. So this is 156. All right. 308, half of that is 154. And so I add 1 to that, I get 155. And so on. 292, I did this. This one is harder for me to do in my head. I got 147. I guess half of 292 is 146, and then add 1. 317, this is an odd number, so for those ones you would divide by 2 and then round it up rather than adding 1. So 317, I got a threshold of 159. The 349 gives me a 175, and the 286 gives me a 144. All right. So these are you have to calculate these one at a time. Individually, though, it's not a hard calculation. All right? Now, we have to sort of actually think for these ones. So this is the important step. It is counting the number of wasted votes. And I hope everybody remembers how the wasted votes works. Every vote for the loser counts as wasted automatically, and every vote for the winner beyond the threshold counts as wasted. So I like to, first of all, I'm just going to circle in each district the winners. Each one I'm circling the bigger number. All right, those are the winners. It looks like the D's won 4, the R's won 2. And maybe it's easiest to just copy out the wasted votes for the losers every time. Remember, every vote for the loser is wasted. So all those numbers which I did not circle over there, they just copy directly into the wasted columns. So 99 wasted for the Republicans in the first one. In the second district, I have 100 wasted for the D's. Then I put the 80 over here, the 146 over here, the 171 over here, and the 139 over here. All right? Any votes for the loser are wasted. So you can just copy the loser votes directly into the wasteds. And what about votes for the winner? This you have to think very slightly. Any vote for the winner beyond the threshold. So what you're going to do is, like in the first row, the winner got 211. The threshold was 156. And so I'm going to subtract 211 minus 156. That's how many extra votes were given to the winner. So in this case, I don't know if I can do that in my head. I got 55 when I subtracted that, which looks right to me. All right. In the next line, 208 minus 155. I think that's 53. I hope everybody sees what I'm doing. And each time I'm taking the circled number minus the threshold. All right. So this line will be 212 minus 147, whatever that is. I did this ahead of time. I got 65 for that one. In the next one, 171 minus 159. I believe that's 12. In the next one, 178 minus 175. I can do that in my head. That is 3, right? They just barely made it to the threshold. 3. And then finally, 147, again, they just barely made it. 147 to 1 versus 144, that's 3 extra. All right, so these are the wasteds. That, I suppose, is the hard step. It's not really hard if you remember what you're doing, although you got to remember what you're doing. All right, the work is pretty much done. We just have to summarize the answer, and remember the answer is always written as a fraction or as a percentage. The way to summarize the answer is we're going to add up all the wasteds. So if you add all the R wasteds, I did this on my calculator, I got 520 for the R wasteds, and the D wasteds, I got 406. So we have more votes wasted by the R's. That means this map is benefiting the D's, at least as far as the efficiency gap is concerned. And then to write our answer as a fraction or percentage, we're also going to add the total of the totals. And that, when I add it up, is 1,862. All right? And so my final answer is a fraction. That big number is the denominator, and then the numerator is the difference of those two. So the efficiency gap is 520 minus 406 divided by 1862. The numerator is always the difference between the wasted totals, and the denominator, the bottom, is always the total of the totals. All right? And if you do the subtraction there, this equals 114 out of 1862. And I put this in my calculator. If you just actually do the division, 114 divided by 1862 is 0.0612. In other words, 6.12%. All right. So the meaning of this is that, of course, both of the parties are wasting some of their votes. What that specifically means is the R's wasted 6% more than the D's did. That's your interpretation of what that percentage means. All right. And we always say the efficiency gap is So I would write this as the efficiency gap is 6.12% in favor of the D's. That's because the R's wasted more, and so this arrangement is beneficial to the Democrats because the Republicans wasted more. All right, and that's how I'm gonna expect you to write your answer. Although on a test or something, you would leave it like this because you wouldn't be able to do that fraction on your calculator, or you wouldn't be able to do it in your head. All right, any questions about that? It's, I would say, fairly straightforward, although there is kind of a lot of steps and you gotta, be sure to remember what you're doing and not mess it up. But you don't have to think abstract thoughts all that much. All right. Great. One last thing that I wanted to mention in terms of the efficiency gap in the real world, it's I think a reasonable question to answer after all of this analysis is like 6%. Is that good, or is this? I mean, this does indicate that the map is 6% in favor of the Democrats. Is that like? Is this an acceptable amount, or does this indicate that something is like super unfair? I will just say, so one thing to say about this is kind of like any statistics, like all stats. The efficiency gap works best when there are many districts. Right, this is just like true in general with statistics. A statistic which is based on only a few different measurements is not actually very useful for much. So when I see this example that we just did, you might say the map is biased in favor of the Democrats, but also just because there were only 6 districts, it might be that just like by some kind of random chance, it happened to be 6%, but it was not because of any kind of unfairness, really. It was just like, it's never going to be perfectly zero. And so anyway, like all statistics, the efficiency gap works best when there are many districts, like, something like 100. So in real life, you wouldn't use the efficiency gap in this kind of a situation. With only 6 districts, it doesn't really tell you very much. It's like, like all statistics works that way. So I will say it's more useful, like in the case of American politics, this is more useful for the sort of in-state representatives. Like I showed a map of Wisconsin last time around. Wisconsin, within the state of Wisconsin, there are, I think, 99 different districts. And so among that set of 99, it becomes a lot more meaningful than just doing it for 6 different districts. It's not all that impressive, and it doesn't necessarily mean anything important. And I will tell you, though, so it's more useful for in-state representatives. A typical sort of fair range is something like 0 to 5%. So when people do this measurement in real life, if the answer turns out to be in this range, 0 to 5%, that's regarded as, okay, that's probably fine, all right? Of course, just like any measurements, you're not, like 0 is, in theory, 0 is the perfectly fair if you get 0. But of course, in real life, you're not ever gonna get exactly 0. You're gonna get some small amount, but it's generally regarded as perfectly fine if you're in the 0 to 5% range. Over 7% is regarded as my kids would say, a little sus. This is according to the experts who measure this all over the country. They tend to get suspicious if the measurement is over 7%. And in fact, there have been some proposals to make it illegal to draw any map where the efficiency gap is over 7%. Although that, I don't believe there are any laws right now that say something like that, but that has been considered. The map that I showed us last time, the state of Wisconsin state reps map, which on an intuitive level, sort of like by the vibes, just by looking at it, it seems like it's been packed. I will say the state reps map, which I showed you last time, which seems super packed, has an efficiency gap of 11%, which is among people who study these things, this is regarded as kind of like absurdly high, extremely high. This is favoring the Republicans, of course. That's what I said last time. And this is regarded as very high by the people in this business. All right. So it is a fairly well respected and often used way of measuring gerrymanders, although not everybody is convinced by it. I think it is a little complicated to explain to somebody, and this is a problem in real life. The people that need to be convinced about these statistics tend to be judges. Like if you think the map is unfair, the usual remedy is to sue the state, and then you have to prove to some judge that the map is actually unfair. And it can be difficult. People have tried to use the efficiency gap. So they actually, they use the efficiency gap in the US Supreme Court to try to argue that certain maps were unfair. And I think it received mixed results. So perhaps you know the Honorable John Roberts, who is the Chief Justice of the Supreme Court. He saw, some lawyer had to explain, this is what this statistic means, this is where the number comes from, and he referred to it as gobbledygook. Is that how you spell gobbledygook? I don't know. John Roberts was not convinced. They had to explain all the math of how this is supposed to be calculated, and he was like, I'm not into that. Lose me with the math. Not a proud moment for the Chief Justice, I would say, but I mean, it is a little complicated, I guess. All right, this is all I wanted to say about the efficiency gap in real life. It is regarded as an important thing, and if you read newspaper articles, even articles in the New York Times or whatever about gerrymandering, they will often mention the efficiency gap as a measure of how good or bad various maps are. All right, any thoughts about this? This is the conclusion of what I wanted to say about the efficiency gap. For our remaining 30 minutes or so, I'm going to talk about the next little thing on our big list. On the big list, you will see 3 measures for gerrymandering. The first was the efficiency gap, which is based purely on the efficiency gap is all about the numbers, right? Like that example we just did in Oregon, I didn't even show you the map, and it doesn't matter if you can see the map or not. It's not about the shapes, it's just about the numbers. We're going to talk about 2 more measures. Will be 2 measures which are all about shapes. Right? Something that we have seen already is that, generally speaking, if you want to draw fair districts, it's not so hard. But if you want to draw lopsided, unfair districts, you have to use ridiculous shapes. All right? And so we're going to talk about 2 different ways to measure how crazy the shapes are. All right? The basic idea is that crazy shapes usually indicate that someone is trying to make them unfair, right? If you are looking at one of these maps and you see a ridiculous, wormy shape, that's probably been drawn in that way in order to cause some kind of advantage to one or the other party. So what I want to talk about are 2 different ways to measure specifically how can we actually measure how crazy a shape is. All right. Actually, there have been several different specific geometric mathematical measurements of how weird a shape is, and we're going to talk about two of them. We'll talk about the first one today. Let me just explain perhaps what I mean. Say that shape from the point of view of this gerrymandering business. If I see a district that's shaped like this seems pretty ordinary to me. I would say this is not too crazy. But if I see a shape that looks something like, something like this, then I think, all right, you're being silly now. Like if somebody draws a district shaped like this on the map, I will immediately think you're probably trying to play some games with the district lines. All right, so this one over here seems crazy to me. All right, now again, we have sort of a vibes problem. Like when you just look at these, I would immediately say, yeah, the one on the left seems totally normal to me, but the one on the right seems crazy to me. And I think everybody would agree with this the vibe check of the situation. But if you want to really, sue the government or something like that, you need to do better than vibes. And so for this reason, we have, mathematicians have come up with very specific ways that you can measure how crazy these kinds of shapes are. So we'll have, like I said, two specific measures. Specific is what I meant to write. Of shape weirdness. And they have fancy names. The first is called the convex hull ratio, and that's what we're going to talk about today. The convex hull ratio. And then the second one has an even fancier name. It's called the isoperimetric quotient. How do you like that? These are two different specific ways that you can measure how weird a shape is. And both of these things are numbers. Like, so on our test or whatever, on your homework, I could actually give you these two shapes and say, tell me what is the convex hull ratio of the one on the left versus the convex hull ratio of the one on the right. And you get numbers, and the numbers are arranged so that sort of like a big number means it's good and a small number means it's totally crazy. That's how these ratios work out. This is where we're going with this thing. So these are numbers, specific numbers. And the way that both of those are set up, they are specific numbers between 0 and 1. 0 means crazy, and 1 means sort of totally ordinary. All right. So these are very convenient ways that you can sort of, you do something or other to the shape to calculate this number. And if you get a number close to 0, that's bad. It means the shape is crazy. And if you get a number close to 1, that means the shape is pretty good. All right. So let's talk about, today I want to talk about the first one, the convex hull ratio. And actually, I don't know if we're going to get all the way to the definition of the convex hull ratio, but let's talk about the convex hull ratio. All right. This is a way of measuring sort of how wiggly a shape is. Let's talk first about this word, convex. You may have seen this word in high school geometry. Everything that we're about to talk about is purely geometric, although there are going to be some numbers eventually when we get to the very end. But some basic geometry, we say a set, I mean like a shape, I'll call it a set, is called convex. This is a simple idea, although it's kind of hard to say in words exactly what we mean, but we're going to do lots of examples to get a feel for it. A set is called convex when, anybody heard this word before? This is something you might have heard of in a geometry class at some point. Like, for instance, my body, like this, is not convex, but My head, just my head, is more or less convex. Anyone know this term? My head, if you look straight at me. If you look on the side, it's not. All right, I'll just tell you what it means. A set is convex when, this is, like I said, a little complicated when you write it down, but when the straight line connecting any 2 points in the set lies entirely within the set. The straight line lies entirely within the set. All right? So in your shape or whatever, any 2 points that you choose inside the shape, the straight line between those 2 points is also inside the shape. This is a weird sounding property, although once you get it in your mind, you can look at any shape and immediately tell me if it's convex or not. So for example, if I have just a square here, is it convex or not? What I am thinking about is it true that if you choose any 2 points in the set, I'll just choose 2 random points like this, is it true that the straight line connecting those 2 lies entirely within the square? And the answer is yes. So this one is convex, and it's because, and it's not because I chose 2 special points, like actually any 2 points inside here, the straight line connecting them lies entirely within the set. Is convex. All right? This is a true fact about the square. Actually, my square is not perfectly drawn. These wobbles down here are a little suspicious. Anyway, what does it mean to be not convex, or like what does that look like? I would say, something like this. This is not convex. Why not? Can anybody describe in words maybe? Can you find 2 points inside the shape so that the straight line connecting them is not also lying inside the shape?
Like the 2 points, like the point on the top. Wait, I don't know how to explain.
Yeah, if we just,
Like
I think
top.
everybody knows what you're saying. If we just choose like 1 point up here
Yeah.
and then another point down here,
Yeah.
then the straight line between them does not lie entirely within the shape, right? This straight line here goes outside. That means this shape is not convex, all right? Let's just, I want to do a whole bunch of simple examples just so that everybody has some intuitive notion. What do you think about this one? You want to show me the thumbs? Is convex or is not? Is means that any 2 points, the straight line is also inside the shape. Everybody's giving me the thumbs up. Yeah, this one is convex. If you choose 2 points here, then anything connecting them is inside the shape. Is convex. Great. How about something like, get a little fancy here, a little hexagon. What do you say? Is convex or not? I say is convex, right? Again, any 2 points inside the shape here can be connected by a straight line inside the shape. This one is convex, all right? I said before, my body, like standing like this, is not convex. That's like if, that shape is not convex. Can you all see how you could choose 2 points so that the line connecting those 2 points does not lie inside the shape? You could you could do this in many different ways, but say take 1 point over there and another point here, right? That line leaves the shape, so this one is not convex. I hope everybody is beginning to get an idea. Yeah?
Well, in this one, couldn't you draw the diagonal line that you've been doing for the other ones?
Yeah, so there are, it's a fact that like this line here actually does lie inside the shape.
Right.
So some of the lines do lie inside, but some of them don't. That means it's not convex. If you read the words that I said up here, the straight line connecting any 2 points lies inside the set. That's what it takes. Yeah. So it's true actually. Like even in this moon here, you could choose 2 points over there, and then the line would be inside. But yeah, the fact that there is at least one pair of points where the line is not inside the set. All right. I said do you agree with what I said before about my head? if you look straight at me, is basically like an oval shape, and that is convex. But the side view of my head, which I'm not much of an artist, but I'm thinking about my nose in particular, that makes it not convex because my nose sticks out like that. And then you can find points here and here, right? This is not convex. All right. Basically, I would say if I were describing this to like a 5-year-old, a convex shape is one where the edge, so convex, I hope you don't feel like I sound silly when I say this. Convex means the shape has no, can I say this word in public? Any curves around the edge. I hope everybody knows what I mean by.
I know.
No? So any, I mean, this is like, I remember, I don't know if kids still talk about this. I remember we used to talk about belly buttons. Some people have an innie, some people have an outie belly button. We don't need to go around the room, but you know, the thing, so by innie, I mean, you know, something like that, right? That part of the curve, this kind of inward bend of the curve, that's what I'm informally calling an innie. And if that ever happens, then the shape is not convex because you can do a little thing like that going across the innie, right? Even if it's just a tiny little innie part, like this whole thing right here is more or less convex, but if I just put a little guy right there, that wrecks the whole thing because now I can put 2 points on either side of this little innie curve, all right? Outward curves are no problem. Like this over here, you could say like this entire part of the shape is like a big outie, a big outward shape facing curve, and that's totally fine for a convex. A convex means there is no inward poking parts of the curve. All right, that's what I mean by this right here is the innie, right? That's what I'm talking about. Convex means there are no innies. It's like all outies, all right? But often outie things tend to also make innies. Like here, you might say, oh, this like head here is like an outie, and that's true. But it creates these innie regions over here. All right. All right. I'm tired of saying the word innie so much. Basically, any sort of real world shape. With wiggly lines will not be convex because of the innies. Like for instance, if I'm going to draw something kind of like a circle, but with like a slightly wiggly edge. So something like this, right? I would say this looks mostly convex, but actually because of the tiny wiggles along the edge, it's not convex because those wiggles, they do produce little bits of innie type curves. Like I can see one right here, for example. There is a slight little sort of inward curve there, which means this shape is not convex. But really, it's only because of these little wiggliness around the outside, all right? If it wasn't so wiggly around the border, then it would be convex. So this is, in real life, typical shapes, they're usually not convex. In order to be convex, it's like the edge has to be kind of perfectly smooth and never bending inwards. So this is all about whether shapes are convex or not, and I hope that everybody has a good idea, and you should be able to just look at any shape and more or less immediately say if it's convex or not. Like this hydro flask right here looks kind of does that, and then it does this. Is that convex or not? No. Why not?
Because the innies.
Because of the innies. Yeah, I see innies up at the top. This here, right? That's the problem. Down here, no problem at all. But this and those two innies are the problem. So this is not convex. But anyway, a real world shape will not be convex, but we can always modify a shape, and this is the important thing about the convex hull, which is really what our measurement is going to be all about. We can always sort of, I will say something like, box in a shape to fill in all the innies and make it convex. All right, for example, what I mean is something like, if I start with that thing, is not convex because it basically has like 3 big innies on this picture, all right? This is not convex, but what I set up here, you can, if you want to, you can sort of box in the shape to fill in all the innies. And what I mean by that is I am going to draw, maybe I'll put this in red. If you were to, say, connect that up and then also include all of that area, then I filled in the innie. So at least that part of it is now convex, even though it wasn't before. If you, using a straight line, go across and kind of fill in that whole innie. And I could fill in the one on the bottom and the one on the other side, and then the whole thing would be convex. So I would do so by making a straight line down here and also a straight line over here. All right. Fill these in, and of course also take the original shape. And now this whole thing is convex. So by adding straight lines to sort of fill in the innie curves, we can make it convex. And this new shape that I get, so I started with this sort of blobby thing with 3 blobs on it. The new shape looks more like a triangle. It has curvy corners, but it's roughly like a triangle. This new shape is called the convex hull. And this is the important idea for the convex hull ratio, is what it's called, this numerical measure of how weird the shape is, all right? The new shape that you get after filling in all the innies is called the convex hull, all right? Here, we're gonna do a bunch of examples. Another example would be something like if I start with like a Pac-Man. What is the convex hull of that? Well, the mouth of this Pac-Man is one big innie, and I'm going to close it off by joining a straight line from here to here, right? And then including this whole area. All right, so here, if I were to, just to be clear about this, if my original shape was this Pac-Man type thing, then the convex hull is, it's like the same circle on the outside, but then instead of that mouth, it has a straight line cutting the mouth, like filling the whole mouth in, all right? I hope it's clear what I'm drawing here. Maybe it's clearer to look at the picture on the left, but the original shape was the Pac-Man. The convex hull is the shape that you get if you fill in all the innies, all right? That's what the convex hull is all about. I have a cute little handout here. I want you to try, so I'm just going to give you a bunch of different shapes. Your job for each one is to draw the convex hull, and they all are just sort of silly shapes like this. You can tell your mom to put this on your refrigerator when you're done. She will be so proud of you doing such silly things with her hard-earned money for your college. If you know what's up, these are very easy to do. Your job is just for each shape, I want you to draw the convex hull. Everybody get one? You should be adding straight lines, kind of like this. Sorry, I wanted to say one more thing before asking you to do this. Another way to look at the convex hull, the convex hull is also, this might help to visualize what you're doing here. I'll draw this one again. The convex hull for that shape would be obtained by adding these straight lines. The convex hull is also the shape that you would get if you wrap a rubber band around Often this is how the convex hull is described in a less mathematical way. It's the shape that you would get if you wrapped the rubber band around the original shape. I hope you all agree. If you did that, you'd end up with these straight lines bridging the gaps, but then it would actually wrap smoothly around the outie curves. All right. Anyway, see if you can draw in the lines to make the convex hull of each of those shapes. In each case, you should be drawing straight lines.
Is this already convex?
Yes. And so in that case, the convex hull
Is this
is the same shape.
Okay. So I don't draw anything on it.
What's up? Good.
I don't know how to do this one.
So you wanna, I see this inward curve, and you
Okay.
wanna just cut across.
Oh, like that?
You could think of it in terms of if you put a rubber band around the shape, where it would go, evenly go around here, but then right there, it goes straight across.
Okay.
The gap. I got mine here. Can we talk about these? These, once you know what's up, this is not hard to do at all. So for the heart type shape, I would go cut straight across the top. Maybe I'll big up my lines a little bit. Straight across the top. I saw some people who also cut a line across here, which I like. That was a slight little detail, but it's true that curve by itself is actually kind of an inward bend. And if you want to be really careful about this, you should fill that part in also. All right. The star, I would do it something like this. I think that's what I would say for the star. All right. Remember, you are just, one way of thinking about this is imagine what it would look like if you wrapped the rubber band around that thing. Every so often I see people do something like, isn't it just like you sort of make a box out of the thing? The answer is no. This is wrong, what I just drew. Because, I mean, if you think about in terms of rubber bands, if you wrapped a rubber band around this shape, it wouldn't do that. It's smaller than that, right? So it should really be something like go across this gap here and this gap here. And I think that's it. This shape. If you like, you could shade in the new shape or just put the outlines. I think I will know what you mean, but it's that shape. All All right, this weird thing down here is going to be joined up like so and so. All right, this sort of, I guess, house-like thing, you have to join up those two parts, but the rest of it is convex. This over here I meant to be a circle, and that already is convex, and so the convex hull, you would not add any new area to this. It already is a convex shape. This one over here, we already sort of discussed that example. You would have to add a bridge across those guys. The triangle also is convex already, and so the convex hull does not add any new area to it. And then this happy little wormy guy, you have to add a big straight line going across like that. All right? This is the convex hull. I hope that makes sense to everybody. Can I just say, I see people packing up your bags. I have one more thing to say though. We got 3 more minutes, right? Just to pull it all together here. What's the point of all this business here? The point of this, like why we care, check it out. If I'm going to try and draw my example that I did before about, this is sort of like a normal shape versus a crazy shape. A crazy shape is like some crazy wormy type thing, all right? Something like that, all right? Check it out. What is the convex hull of each shape look like? For the normal shape, if I were to make the convex hull, I have to add in a few little things to just bridge the gaps on all the little wiggles, all right? But it's really not much that I'm doing here. Maybe there's little ones up here, right? I think I filled in, there's another innie right there. Anyway, it's just like tiny little innie regions that you would have to fill in if you want to make the convex hull. What about the convex hull on this thing? Actually, this requires big additions of new area. I think I'll have to go all the way across here, all right? Right? We actually have to add a lot more area to this one than we do for that one. And so the moral of the story here is a nice shape, a nice normal shape, has the convex hull, I'm going to write CH for convex hull, only slightly bigger. This is like the shape on the left there. It's fairly normal, and what I mean, the vibes of normal, technically speaking, I feel like that's normal. It's because the wiggles are not so big. And if you want to fill in all the wiggles, it only takes a little bit of filler. Versus this crazy one over here, you have to fill in a lot. So a crazy shape has the convex hull much bigger. And this is how we can use the convex hull to measure how crazy a shape is. All right? So next time we'll talk the real definition, but this is the basic idea behind why anybody cares about the convex hull in the context of gerrymandering. All right, that's all I wanted to say. Like I said, I have the homework printed out here, so I will hand these out, and then we'll be on our way.